All right, just a real quick review of what we did yesterday. We had a line segment, so I'll put a dot at one end and a dot at the other. Those are my endpoints. Then I looked at this and I said, let's say right there, I'll put a little dot. I'm guessing right in there might be the midpoint, somewhere close. May not be exact, but it's close enough. All right, and then what do we do from that midpoint? We did what? We drew a line, just any line like this, any line like that. Okay, well that's up, that's up, that's up. We don't say straight up, we say perpendicular, perpendicular, okay? We say perpendicular. So watch. That's perpendicular. I said this was the midpoint, right? So what's true about this situation right here? What's true about AM and MB? They are equal to each other. Okay, so what did we just draw? This line right here is a perpendicular bisector. Okay, everybody listening? A lot of chatter going on. Let's settle down. All right, it's a perpendicular bisector. So we did that with a line segment. You can't do that with a line, because watch, if I had a line, what's the difference between a line and a line segment?
A line goes on and on forever.
That's right, that's right, line keeps going on and on forever. So is that the midpoint of a line? Is that the midpoint of a line? Because what does it mean? A midpoint splits it into two equal parts, right? So watch. Look, from here to the left is forever, isn't it? From here to the right is forever. So really, any point on here you could kind of think of as the midpoint, couldn't you? All right, because there really is no midpoint to a line, but there is a midpoint to a line segment. What we're going to do now that you know about perpendicular bisectors of a line segment, now what we're going to do is we're going to use a triangle. Just happen to have a triangle right here. And we're going to find the perpendicular bisector of all three sides of this triangle. And let's see what happens to those three lines. Actually, I got ahead of myself. Let's do this. This is just real quick. Let me just introduce a word to you that you probably haven't heard before. If I had two lines and they do this, any two lines that are not parallel, or even not skew, but any two lines in a plane, it's a problem. Any two lines in a plane, if they're not parallel to each other, what will they always do? They'll always intersect each other. Very good. Okay, two lines will always intersect each other as long as they're not parallel to each other. You follow me? All right. Now, what if I had, that will always be true. But is that always true about all three lines? If I have three lines, do all three lines intersect each other at the same point?
Yeah.
No, they don't. But if I took this line and I scooched it over to right there, okay, that's pretty close. Let me try to get a little bit closer. That's close enough. All right, won't hit dead on. But if I had them all intersect, and they all intersected at the same point, you follow me? So if I have three or more lines that intersect at exactly the same point, I have a word for that, and they are called concurrent lines. And we're going to refer, the next two lessons deal a lot with concurrent lines. So if I say the three lines are concurrent, then you need to know what I'm talking about. They all intersect at one point. Everybody see that? They all share that same point of intersection. All right, that was pretty easy. That's just a little vocab, because what we're going to do now, we're going to get a little bit more specific, and this is where we're going to go with the triangle. And we're going to talk about concurrent lines. So the very first lesson we talked about was perpendicular bisectors. So watch. I'm going to take the perpendicular bisector of all three sides right here. Let's just name them A, B, C. All right. And where do you want to start? Let's start with BC. Let's find the perpendicular bisector of BC. So the first thing we're going to have to find is the what? Well, the midpoint, right? Because we want to bisect the segment. Okay. So when you find the midpoint. Now, I don't really have a good way on here to see exactly where the midpoint's located, so we'll just kind of figure out. Do you think that's pretty close, or where should I go? To the left? The other left? Okay, that would be the right. All right, so
Right there.
right there, does that look like midpoint? I'll tell you what. You know what I'm going to do?
Yeah. Measure it.
You do know what I'm going to do?
What are you going to do?
I'll just show you. Watch. See, if I click like that, see that dot right there? So
That's the left I was
so it would be actually just a little bit to the left. Some more. Yeah. So it's about in there, isn't it? I went a little too far. I know. All right, there we go. Good enough. All right, let's do the same. Now on this one, it's a little bit harder to see. Oops. So that would be about right there, wouldn't it?
Yeah.
Okay. And then put a little dot right there. All right. And then,
Right about there.
so if I go straight across, straight up and down there, it'd be right there, wouldn't it?
Yeah.
Okay. Now, oh, it went to black. Let's go back to red. Okay. All right, so now what do I want to do? I want to make a perpendicular line, don't I, from that midpoint? So I'll go perpendicular right there. And that's perpendicular. And I want to go perpendicular to this. About right there. Now I'm going to have to eyeball this, but look at this angle right here, and we'll draw it till it looks perpendicular. That looks pretty close, doesn't it? Maybe a little bit more this way. It's pretty close. All right, so let's say that's perpendicular. Now watch. Let's draw the perpendicular bisector of this right here. So what am I going to do? I'm going to put my line starting right here at the midpoint, and I'm going to go perpendicular. Now, guess what's going to happen to this? We just talked about concurrent lines, didn't we? So what do you think might happen here? It's going to cross. That's right. If I draw it so it's perpendicular, now if I was very accurate, I was semi-accurate on this. I had to eyeball a couple of these, okay, but I was fairly accurate. They're going to intersect each other at a common point. By the way, that common point is called the point of concurrency. Okay, when three lines are concurrent, we call that the point of concurrency. But check this out. What did I just draw? I just drew perpendicular bisectors of all three sides, didn't I?
Yes.
And they all intersected at one common point, which is kind of cool. Okay, so it's right here. We actually have a name for that common point. I'm going to tell you. We call it the Circumcenter. Well, the point of concurrency is the word that we use for any three lines that intersect, okay? So that's kind of a general word, but this one, let's stop talking and listen, please. But this is more specific. This is the point of concurrency for lines that are perpendicular bisectors of a triangle. Make sense? So we call that point right there the circumcenter. That's the name of that point. The lines aren't called the circumcenter. The angles aren't called the circumcenter. What's called the circumcenter? The point itself. And we'll call it P for point. Is that all right? All right, so that is the circumcenter. Now, how did we find the circumcenter? We made what? We made perpendicular bisectors of what? Of the sides of the triangle, right? So write that down. So in order to find the circumcenter, we took the three sides and we found the perpendicular bisector of all three sides. Keep this in your notes. It's important that you have this in your notes so you can go back on it, because my honors class just finished chapter 5, and this is the first section, right? These are going to be the first two sections, and we're going to have a lot more other stuff after this, and a lot of them forgot this stuff because it was earlier in the chapter. But they could always easily go back to their notes and see it, and it's right in front of them, so they can review a little bit better. All right, so make sure it's in a notebook, and make sure that you label it very, very carefully. So circumcenter, how do you find it? You find it by taking the perpendicular bisector of all three sides. Get it? And how do you find the perpendicular bisector? You find the midpoint, and then you make a perpendicular line from that midpoint. Here's another midpoint. Make another perpendicular line from there. Here's the third midpoint of the other side. Make a perpendicular line there. If you are accurate, okay, all three lines are going to intersect at one point. If they don't intersect in one point, guess what? You weren't what? You weren't accurate. I said, if you were accurate, follow my reasoning. Listen, Blake, head up. Follow my line of thought. I said, if you were accurate, then they're going to all intersect in one point. If they don't intersect in one point, guess what? You were not accurate. Very good. Okay, you're following along. Okay, so let's do this. Here's one other thing that's special about this point. This point is called the circumcenter. That's kind of special that it has its own name, but it's even more special than that. Okay, watch this. Let me make another color. If I started at the circumcenter, and if I drew from that circumcenter to each of the vertices, what are my vertices? Yeah, give me letters. A, B, and C. Okay? So if I if I went from point P, that circumcenter, and if I drew a line to B, and I drew a line to C, and I drew a line to, what do you think? A. What do you think might possibly be true about those three blue lines right there? They kind of look like they're what? The three blue lines, come on. What does it look like? Geometrically, what does it look like? It looks like they are congruent to each other, right? Okay, it looks like they're equal to each other, and they absolutely are, all right? We're not going to go through a proof to show you why they are. Just believe me that they are, okay? So watch. This segment right here, this one right here, and this one right here, okay, they're all congruent to each other, all right? So if you read the book, what the book basically says is the circumcenter is equidistant. What does that mean to be equidistant? The same distance, right? The same distance from the three vertices. Okay, it's a lot of words, it's a lot of vocab, it's a lot of geometry words, but listen to what it says. It makes sense, doesn't it? That the circumcenter is equidistant from the three vertices, which means from P to B is the same as from P to A, which is the same as from P to C. Everybody see that? All right, that's what's true about the circumcenter. So let's write that down. So AP must equal what? BP, which must equal CP. All right, so those three lengths must be equal to each other. So you can kind of see what they're going to do in the book, right? They'll say, all right, P is the circumcenter. BP is equal to 5. What's the length of AP? 5. It's 5. That's right. You can just look at it. But you have to know that those are equal to each other, right? Now, in the book or on the test, it's not going to be nice, pretty colors. It's not going to be the blue line and the red line. You follow me? Okay, they're just going to be all the same color lines, but you got to know from the point to the vertices are the same distance. So if that's 5, and that would be 5 as well. Make sense? Now you know what they're going to do. You've seen this over and over and over again in these chapters. They might make this like 3x plus 2, and they make this one like 5x minus 4. I don't know if these numbers will work, so don't even plug these in, okay? I'm just making stuff up. They're not telling you the lengths, okay? They just say this. Now, would you be able to find the lengths if they told you this information? Yeah, because what would you do with 3x plus 2 and 5x minus 4? You'd set them equal to each other, right? You would set this equal to this, all right? Solve for x and then do what to it? If you want to find the lengths of it, plug it back in. That's right. Okay, then you... Does it... Oh, so it does come out nice. Yep. That's 2x and that's 6. And yep, so x equals 3. So it did work out nice. So what would the length of AP be then? If x is 3, what would the length of this be? How about 11? 3 times 3 is 9. Okay, plus 2 is 11. Put it in here. 5 times 3 is 15 minus 4 is 11. So what would BP be without knowing any numbers or letters or anything?
11.
It's got to be 11, right? Because they're all 11. Make sense? You kind of see what they're going to do, don't you? On the homeworks? Okay. All right. Enough of that. Let's go on to the next video since we're running out of time here, and we'll do one more thing. Are you listening? We'll do one more thing. This time we found the perpendicular bisector. On this next one, we're going to do something else with it, and you'll see when we get there.